Hello, welcome to another module in this massive open online course on Bayesian MMSE estimation for wireless communications. All right. So far we have looked at the MMSE estimate, all right, and we also looked at how to compute the variance or how to compute the mean squared error of the estimate of the MMSE estimate. All right. Now let us look at a new framework to calculate the reliability of the MMSE estimate, or basically calculate the number of samples or number of observations required to achieve a certain degree of reliability in the MMSE estimate, all right, or in our estimation process. Okay. So today we are going to focus on basically a framework to characterize the reliability of the MMSE estimate that we have thus far computed. Okay. So reliability of the MMSE estimate. Okay. And recall that for a Gaussian parameter h, Gaussian parameter h given a Gaussian observation vector y bar, Gaussian such that h comma y bar are jointly Gaussian, then what we have is basically, so also this is also important, we have h comma y bar, this has to be jointly Gaussian. Then we have expected value of h given y bar, all right. This is the MMSE estimate equals h hat. In fact, we have shown that this is the MMSE estimate. In fact, in the very first few lectures, we have derived the expression for the MMSE estimate, and we have shown that the MMSE estimate is nothing but the expected value of the parameter h, given the observation vector y bar. Okay, that is the expression for the MMSE estimate. Further, the MSE, the mean squared error, that is expected value of your h hat minus h whole square given y bar. I am not going to write this explicitly because the estimate is calculated only conditioned on the observation vector y bar. This is basically your RHH minus RHY bar, expected value, the cross covariance expected value of h times y bar, covariance inverse of the covariance matrix times R y bar h. Okay. So, what we have therefore is basically that your h given y bar, this is Gaussian, correct, this has a Gaussian distribution with mean h hat given by the MMSE estimate, okay, and variance given by nothing but the mean squared error, that is your RHH, RHY bar, RYY inverse, RYH. Okay. This is also known as the posterior probability density function. Okay. We have the prior, this is also known as the posterior this is also known as the posterior probability density. The mean of the posterior probability density is basically your h hat, and this is basically the variance. Okay. So, basically what this says is, given the observation vector y bar, the true parameter, that is given the observation vector y bar, the true parameter h, correct, it is distributed as a Gaussian, conditioned on the observation vector y bar, it is distributed as a Gaussian with the mean centered at h hat, that is expected h given y bar is h hat, and the variance is given by in fact the mean squared error, that is r h h minus r h y bar times r y y inverse into r y bar h. Okay, correct. For example, consider our wireless sensor network estimation problem. For example, considering again our WSN, the WSN estimation scenario, correct, the WSN estimation or the wireless sensor network estimation problem we have, that is what is our wireless sensor network the WSN estimation problem. Recall that the WSN estimation problem is y bar equals 1 bar, that is the n dimensional vector of all ones, 1 bar times h plus v bar, where v bar is additive white Gaussian noise. We have the estimate recall that the estimate h hat is 1 bar transpose y bar divided by n by sigma square divided by n plus the prior mean mu h divided by sigma h square divided by 1 divided by sigma square n plus 1 divided by sigma h square. This is the estimate, this is the MMSE estimate, this is also the mean, this is the your MMSE. Recall that this is the MMSE estimate. Okay, and this is also the mean, this is also your posterior mean, that is expected value of h given y bar, this is also equal to h. Okay. And further the variance, now if you look at the variance, that is the mean squared error in this case is nothing but the variance of the posterior, that is expected value of h hat minus h whole square, this is equal to, and we have derived the expression of this, that is 1 over sigma square divided by n plus 1 over sigma h square. And you can see this is we have derived in the previous module, this is the harmonic mean of the MSE, that is ML mean squared error, comma prior variance, that is sigma h square. ML mean squared error, that is sigma square divided by n, and the prior variance, that is sigma h square. Okay, this is the harmonic mean of the mean squared error of the ML estimate and the prior variance. Okay, and therefore, now you can also observe an interesting thing, that as n increases, now let us look at the behavior of this. As n increases, let us look at the behavior of this. As n increases, observe that sigma square over n decreases. Therefore, 1 over sigma square over n increases, 1 over sigma square over n increases. Therefore, the denominator increases as n increases. Therefore, the denominator increases as n increases implies MSE or variance decreases. Okay. Okay. So, it is easy to keep it is important to keep that in mind. What we are saying is as n increases, this mean squared error decreases, all right. And remember, the mean squared error is also the variance of the posterior probability density function, which means, remember, it is a posterior probability density function is a Gaussian. So, as the variance as n is increasing, this variance is decreasing, which means that the true parameter h, correct, comes closer and closer in a probabilistic sense to the mean, which is the estimate h hat, because you can see that the variance is decreasing as a function of n. So, even though we cannot say that it is always going to be close, the true parameter h is always going to be close to the estimate MMSE estimate h hat with a very high probability, that is to a very high degree of certainty, the true parameter h hat is the true parameter h is very close to the MMSE estimate h hat. We are going to see that slightly later using a pictorial description of this, okay, right. So, the variance is decreasing. Now, one can therefore ask the question, what is the number of samples required for a certain degree of reliability, and we are going to characterize this. What is the number of samples required what is the number of samples required so that the probability that h hat lies within sigma 2 of true parameter, sigma by 2 of the lies within a distance of sigma 2 of the sigma by 2 of the true parameter h is greater than 0.9999, or basically you can say in a certain sense achieving 99.99% reliability. So, we are asking this question, what is the number of samples n? Remember, we are characterizing the number of samples, or basically number of samples is basically the same as your number of observations. Another word for that is basically your observations. What is the number of samples or observations n required so that the probability that the true parameter h lies within a sigma by 2 radius of the estimate h hat, or the estimate h hat lies within a sigma by 2 radius of h is greater than 0.9999, or basically we can say that we have achieved 99.99% reliability. Okay. And so, if you want to represent it pictorially, this is our posterior Gaussian distribution, and the mean is basically of this posterior is h hat, correct. And therefore, what you can see is basically if we draw a sigma by 2 radius, if we consider a sigma by 2 radius around this thing, for instance, this is, let us say, your, so this is your h hat plus sigma by 2, and this is h hat minus sigma by 2. So, the true parameter h has to lie within this sigma by 2 radius. So, true parameter h has to lie within this sort of box with probability greater than with probability greater than 99.99%. And what we are saying is that therefore, this h has to lie within this sigma by 2, that is h hat plus sigma by 2 to h hat minus sigma by 2 with probability greater than 0.9999 or 99.99% reliability. And you can now see that as n is increasing, this variance is decreasing, alright. So, basically the Gaussian will become increasingly more and more concentrated around h hat, which means the probability that it is closer to h hat keeps increasing as n is increasing, alright. So, as n increases, the probability that h hat lies within this sigma by 2 ball, the probability that h lies within the sigma by 2 ball around h hat progressively keeps increasing. And what is, and we want to find that n such that this probability is at least 0.9999 or greater than basically 99.99%. Okay, so that is what we have to find, and we can proceed with this as follows. Okay, and this is an interesting problem. So what we need is basically we need for our given degree of reliability, we need, that is magnitude h hat minus h less than or equal to, the probability that magnitude h hat minus h is less than or equal to sigma by 2 has to be greater than 0.9999. Okay, this is what we need. Okay, fine. Now this implies that the probability that this it lies outside this ball, that is probability magnitude h hat minus h greater than or equal to sigma by 2, probability lies, this is the probability it lies, h lies outside the ball, probability h lies outside the sigma by 2 ball. Naturally, if h hat minus h is less than or equal to sigma by 2, it lies inside the sigma by 2 ball, and magnitude h hat minus h is greater than or equal to sigma by 2, it lies outside. So, if the probability it lies inside is greater than or equal to 0.9999, it means that the probability it lies outside has to be less than or equal to 1 minus 0.9999, which is equal to 0.0001. That is basically your 10 to the power of minus 4, and that is also very simple to understand, because what we are saying is that the probability that it lies outside the sigma by 2 ball has to be greater than or equal to probability that it lies inside this sigma by 2 ball has to be greater than or equal to 0.9999, which means the probability that it lies outside this ball has to be less than or equal to 1 minus 0.9999, which is basically 10 to the power of minus 4. That has to be the case, because the sum of both these probabilities, probability lies inside the ball and plus probability lies outside the ball, has to be equal to 1. So, one is greater than or equal to 0.9999, which means the other has to be less than 1 minus 0.9999, which is 10 to the power of minus 4. Okay. So, it is very simple, and now look at this, we have this h hat minus h. Now, this is basically, you have to realize this is nothing but your estimation error. Because we have h equal to the true parameter h hat equals the estimate, that is your MMSE estimate. So, we have h hat minus h, that is the estimate, we have h hat minus h equals estimate minus true parameter minus your true parameter, and this is equal to W, which is the estimation error. Okay, so this is W, which is the estimation error. So basically now we are asking this question. So basically now I can replace this H hat minus H by basically this quantity W, and now basically we are asking this question that what is the probability, right? We have probability that this estimation error magnitude W greater than or equal to sigma by 2 has to be less than or equal to 10 to the power of minus 4. Okay, so that is the question that we are asking. Now recall that your H is Gaussian distributed with mean H a hat and variance 1 over, okay, we have already seen this for the wireless sensor network. H is distributed, this is the mean, posterior mean H hat, posterior mean which is given by H hat, and the variance which is given by the MSE, that is 1 over sigma square by n plus 1 over sigma H square. Okay. And therefore, what we have is, if we look at this now, so now let us denote this quantity by sigma tilde square, this quantity, that is sigma tilde square equals 1 over sigma square by n by 1 over sigma H square. So I can say H is distributed, the posterior distribution, in fact I have to say H given y bar, this is the posterior distribution, is Gaussian with mean H, variance sigma tilde square, and therefore now this implies that if I look at this error, that is if I look at H minus H hat, okay, so this is basically H minus H hat. So this is from the parameter I am subtracting the mean, which means this makes the mean 0. So this is distributed as a Gaussian with mean 0, variance sigma tilde square. So this is basically your H minus H hat, which according to our definition is minus W. So what we are doing, so H is distributed as a Gaussian with mean H hat and variance sigma tilde square. What we are doing is from now from H, right, we are substituting H hat, we are substituting the mean. So naturally what happens, the mean becomes 0 and therefore it is distributed as a Gaussian with mean 0, variance sigma tilde square. From a Gaussian, if you subtract the mean, it becomes it still remains a Gaussian, but it is a 0 mean Gaussian with the same variance. Okay. So W minus W is Gaussian with mean 0, variance sigma tilde square. Now that also implies, correct, that also implies that W minus W is Gaussian, W is also Gaussian with mean 0, variance sigma tilde square. Since W is minus W is Gaussian with mean 0, variance sigma tilde square, W is also Gaussian with mean 0, variance sigma tilde square, correct. Okay. Mean equal to 0, the mean equals 0, and therefore now you can write the probability density function of this estimation error W, which is equal to basically 1 over, this is Gaussian with variance sigma tilde square, 1 over square root of minus 1 over square root of 2 pi sigma tilde square e raised to minus W square divided by 2 sigma tilde square. This is the probability density function of W. Okay. This is the probability density function of the estimation error W. Alright, so we have the probability density function which is characterized by the Gaussian random variable with mean 0 and variance sigma tilde square. Okay. So what we have done in this module so far is basically we have started to develop a framework to characterize the reliability of the MMSE estimate for this scenario of Gaussian parameter estimation, where H the parameter h and the observation vector y bar are jointly Gaussian. We said that the posterior probability density of h is characterized by the mean h hat and the variance which is given by the MSE. So, what we have framed is we have framed an appropriate problem as the minimum number of samples required to achieve 99.99% reliability, and now we have characterized the probability density function of the estimation error W as a Gaussian probability density function, alright. So, we will stop this module here and complete this derivation in the subsequent module.